right. Give me a minute to bring up the live stream on my phone to make sure the audio is there. Apparently it is. So there's one thing I forgot to open. Okay. We talked about instance centers. And we did a problem based upon that for a minute. Now we're going to move on down to accelerations. And there is good lectures on Blackboard already that I did, but I'm going to sort of accentuate them a little bit here. So what you've got is a similar equation than what you had with velocity. In other words, you had VB is equal to VB relative to A plus VA. Now, if I just go in and replace that with acceleration, you get essentially the same equation, except this term has two components. There's a component in which if you're sitting, okay, we have to remember what this term is, the acceleration of B relative to A. In other words, you are sitting right here on A, looking at B, and saying, how is it accelerating relative to me? So, how is it? It's either spinning around, and it's spinning at a certain rate around you, and then a few seconds later it's spinning faster, and then faster, and then faster. So you've got that component. That is the tangential component. Then the fact that, or if it is at all spinning about you, then you've got the centrifugal part. Essentially the v squared but over r, but maybe listed this way. But in any case, we go down here, you actually have what's commonly called the centrifugal. Now he's got this thing spinning the other way than what I did, but the alpha is the acceleration of the omega. In other words, and it's simply that. Now, you have two terms. As you go through this, you find out these two terms look very much like this. Here's the one term, and this term is the centrifugal term. Omega squared r. Now, if you think about it, you can get that out of that, and I talk about that in the lectures. So from this perspective, let's go in and take that one problem we had that we did with instance centers, and then we turn around excuse me, we turn around and did that one, instance centers, on Monday, or Wednesday. No, maybe that was Monday. We did that instance centers on Monday. On Wednesday, we did it in the classroom because the air conditioner started working again. And we did it this way. Well, we did this. And we went through the links that way, and you can look at that video. And now we're going to take that same problem and we're going to go forward with it and look for the accelerations. So I'll leave this page up because I'm going to come back and reference it. And at this point, let's head off back over here. Let's find that last page. Okay. Now, unfortunately, the picture is the picture. It looks like I may need to repeat what I did the other day. But instead of repeating, I'm going to go back and grab some information off that lecture. But if I'm doing that, I'm going to grab the picture, copy. I'm going to go ahead and put it back down in a new location. Looks better that way. So I think what we found was omega was equal to 1.24 radians per second. And I think we found now maybe I should go back to the picture that I had a second ago. Okay, so what we ended up finding was that, and omega BC is rotating that way. How about 2.2? We'll just take it as 2.2. Omega BC is equal to 2.2, and it is doing this way, and it is doing this way. Okay, go away. Okay, now let's say he said that this thing was going north at a velocity of 12 inches per second. Let's say in addition it has an acceleration of 1 inch per second squared at this instant. So what is alpha BC? What is alpha AB? So how do we do this? Excuse me. We sort of mimic what we did on the board last time. In other words, I have a link A to B, and I have a link B to C. Now here on this particular medium, I can separate them a little better. On the board, I was kind of compressed. Acceleration of B is equal to the acceleration of B relative to A plus the acceleration of A. Since point A doesn't move, that's pretty easy. Now, how is the acceleration of B? Well, it can occur two ways. If the arm is speeding up, in other words, it has a certain speed, but later it has a faster speed, then you will have alpha and across R, and then R, B relative to A. But that's not all. The fact that it's spinning means that this point has a centrifugal component. If you go back and look, there's your centrifugal component. And I guess he generally puts this one is listed as the magnitude. And in our case, that's the magnitude. And this is the direction with a scale on it. Now, if you list in your numbers, and then we did this the other day, but I'm going to do it again. And then I guess I'll save a place for this later. Or B relative to A simply means draw a vector like this. And what is it? Well, it's 5 over square root of 2I, because this is 45 degrees, and it goes down 5 over square root of 2j. I'm going to go ahead and do this vector since I'm here. That is R, C relative to B is going to be 4 cosine 30I, meaning you go out here, that distance, plus 4 sine of 30j. These are the two vectors that we're going to use, one in one equation and one in the second. So, with that, back down in here, 5 over square root of 2 minus 5 over square root of 2 and 0 minus, okay, at this particular point, I'm going to go ahead and use this 1.24 squared, and I'm going to simply list this vector down because that's what he wants. Now, here in this particular component, I'm going to get an I and a j component, but no k. So my I component will come from the cofactor expansion of that. Root 2. And then let me give that a minute to come up. All right. Now, the reason I brought it up is because I'm going to figure out these components in a numerical sense. And that's 1.24 times 5 divided by the square root of 2, 4.38. I'll just stop it at that, 4.38. Except I forgot to square it. .44. 5.44. I make sure this copied down. Should have had a minus sign right there. Run back up, run over to the side. Okay, so I get minus there, I get plus there. Hang on. Reason they're the same is because this is the same as that multiplied by that number. Okay, that times that minus that times that. That times that minus that times that. There's already a minus. Okay, you have this whole thing listed here, and what you have unknown here is these two. Next, we need to, so what I'm saying is this is only the intermediary part here. We have another part that we've got to do, and that is we need to go at the next link. Unfortunately, the picture is such that it might be best now to go ahead and make use of my ability to copy things over to the side and come back on board here. Okay. So, acceleration of c, let's zoom in on it. Acceleration of c is equal to acceleration of c relative to b plus the acceleration of b, which in fact is that, but I'm not going to put it in there quite yet. I'm going to work out this first. I can go ahead and identify one particular part here, and that is if it truly is accelerating this way, and that is the vector form of it. Now, let's mimic what we've got here. BC, which I do not know, cross RC to B, which I do know, right here, minus omega BC, its magnitude squared, times RC to B. Excuse me. So I can continue instead of writing this is my shorthand for cosine 30 for sine 30, 0 minus from the previous problem we got about this value, so I'm just moving it up to 2.2. And then this, so I'm going to do shorthand here. 4 cosine 30i plus 4 sine of 30j. Now, again, you only have I and j components here. Cofactor expansion. So in the j, so I'm pulling out the I. The I means you get rid of that, and you get rid of that. So that should be a sine. The j component, you get rid of that, you get rid of that. 4 cosine 30. Now, I can stop and calculate all this out. Okay. 2.2 squared times 4 times cosine degree 30, 16.77. And minus, so I got to get this one times that. Next, all I need to do is change that to a sine. 9.68 j. 1j is equal to that. Now, one of the things I didn't do, I'm going to go back and do this in red. here. So at this point, I should have carried this AB, and in a minute I'm going to put it in there, but for the time being I'm going to hang one more time. 1J is equal to that minus that minus alpha BC for sine of 30 I. The J is that minus that, but the minus minus gives me back a plus for cosine 30 minus 16.77 I minus 9.68 J. Here is where I'm going to join these things, because now I'm going to grab this one, replace it here, and I'll have one giant equation with two unknowns. One of the things I should have done that I did not do, and if you notice it, I had the alpha AB here and alpha AB, and I dropped the AB for some reason. So I'm going to put it back. Now I'm going to combine them. Alpha AB I plus 5 over square root of 2 alpha AB J minus 5.44 I plus 5.44 J. So I've got one huge equation with one unknown and two unknowns. How do I get that solution? Well, here's what I do. I identify all the i's, and then I identify all the j's. Well, and with that, I realized I'm pretty sloppy today, but that should have been a J, and as a result, it fits in there. So if we color code this, we see this whole equation, either we have a blue or a green. So let's do the blue first. The blue is going to be the I. So here's my I terms. On the left I have 0. Then I have minus, well, I'm going to go ahead and do it this way. Alpha BC for sine of 30. Looking for the next blue. Minus 16.77. Okay, looking for the next blue. Plus 5 over square root of 2. Alpha AB. Looking for the next blue. Minus 5.44. Did I have the right number of terms? Over here I have 1, 2, 3, 4. 1, 2, 3, 4. And on the left I have no terms, which that's why you have a 0 here. So I have one equation. Let's look at the green term. Green term is a J, and it gives me 1. Why 1? Because that's what's right there. Equals to, next green term, alpha BC, 4 cosine 30. Next green term, minus 9.68. Next green term, 5 over square root of 2 alpha AB. Next green term, 5.44. Have two equations, two unknowns. Me, I like matrices because MATLAB likes matrices, and because MATLAB lives in matrices. So what I'm going to do is I'm going to make a matrix. I'm going to change it here. Here's my matrix. Okay. What are my unknowns? Alpha AB and alpha BC. So there's got to be a right-hand side to this as well. Okay, so let's start working here. Okay, let's look at all the coefficients in the I equation, or in the blue equation, that are associated with AB. It would only be 5 over square root of 2. Looks at all the coefficients of this term. That would be this term. It should be minus 4 sine of 30. And I'll go ahead and put it back in complete form. Now, looking in the J equation, I'm going to look for the coefficients of alpha AB. 5 over square root of 2. Alpha BC in the second equation, 4 cosine of 30. All the terms that sit on the other hand of the equation. Well, at first you'd say it's 0 and 1 by themselves until you realize, hey, wait a minute, this term and this term could be moved over there. So I'm going to move them over there. Plus 5.44, they change signs when they move over. Plus 16.77. Then on this one we have this term and this term. Again, they change signs. Plus 9.68 minus 5.44. If I solve this matrix, I solve alpha AB and alpha BC. Let's do it real quick. Okay. So, matrix, call it K, equals to 5 divided by square root of 2, and then space minus 4 times sine in degrees of 30. Next line, 5 divided by square root of 2, space 4 times cosine degree of 30. Close the brackets. There's my matrix. That's what sits on the left-hand side. Right-hand side, 0 plus 5.44 plus 16.77 Next row, 1 plus 9.68 minus 5.44, close bracket, hit the enter, I get that term. So now if I do the inverse of k times right hand side, that's your solution. Okay, 4.42 and minus 3.3 roughly. So what does that mean? Okay, alpha AB being 4.42 means that this link is accelerating in that direction. Alpha is equal to 4.42. What does that mean on this other one? That means it's not going this way, it's going that way. Or you could say decelerating, and it's minus, okay, alpha BC minus 3.3. The key to these is systematic. You stay systematic and break them into their components. And technically, I could have said this is kind of the corollary to that, but we combined them here, broke them by components, ended up with two equations, two unknowns, solved our two unknowns. So I think that's pretty much it. There's not much more I can do, and with the time left, which is only a few minutes, and we'll go from there.